Hello all, welcome to Code Hub. Today let us solve the lead codes daily challenge and the problem is count complete tree nodes. Given the root of the complete binary tree, return the number of nodes in a tree. According to Wikipedia, every level except possibly the last is completely filled in a complete binary tree and all nodes in the last level are as far left as possible. It can have between 1 and 2 bar h nodes inclusive at the last level h. So design an algorithm that runs in lesser than order of n time complexity. So obviously to count the number of nodes in a given tree, this is a complete binary tree. What does it mean is the complete binary tree will be having at most two nodes, but in the last level if there is not it is not the two nodes, then it will be as left as possible. As you can see that it is as left as possible. So this is what the condition for complete binary tree. So we have to count the number of nodes in this given input tree. The number of nodes are 1 2 3 4 5 6. So the output is 6, and in the second example there is no node at all, so the output is 0, and in the third example the output is 1. But can the time complexity, the approach that we can do here is order of n, which is we can do a in order, pre-order or post order traversal, and we can find the number of nodes. We can have a counter to count the number of nodes that we are visiting in the complete binary tree, and the time complexity will be an order of n, and the space complexity will be an order of n if auxiliary stack space is used in recursive calls. So how can we do this better? Yeah, we can do this better lesser than 10 order of n time complexity. How can we do that? We can make use of the property of complete binary tree. I will say the property what we can follow. So before I have said the space complexity will be an order of n, but it will not be an order of n. It can be said as order of L, where L will be the depth of the tree, or you can say it as order of log n, the recursion stack space, because it cannot be a skew tree in this question. So it is a complete binary tree. So definitely it is not going to be a skew tree. So that we cannot say the space complexity is order of n. So we can say it as order of L. So now let us try to optimize this. So let us take this example. Let us copy this image and try to paste here. Mm. Consider we are having a tree something like this. So how can we compute the number of nodes in this particular tree? In this particular tree, we can go like this. In order traversal 1 2 3, we can just go and visit their nodes and we can compute the new trees. But you can see that in complete binary tree, the tree is going to have the nodes as left as possible. So we can know that the if there is a complete binary tree like this, as you can see that this is a complete binary tree of size 3. The nodes in this tree is 3. So how can we say this this complete binary tree is having node 3 without visiting the all the three nodes? Without visiting the all the three nodes, we can say by using a formula like 2 power h minus 1, where the h is going to define the height of the tree. The height of the tree, as you can see, the height of the tree is 2. Considering this node has a height is 1 and this node's height is 2. So as you can see, the height of this complete tree is 2. So 2 power 2, which is 4 minus 1, which is equals to 3. 4 minus 1, which is equals to 3. So without visiting all the nodes, we can easily say the number of nodes if this is going to be a complete tree. So we are going to write a function, write a recursive function, which is going to say if this subtree is a complete tree, then we can just apply the formula 2 power h minus 1 and just return the number of nodes in that subtree. Or else we can, what we can do is, if we are having a tree like this, as you can see, this is not a complete, so this is not a complete tree. As you can see, this is not a complete tree. If this is not a complete tree, what we can say is we can add this as the number of node at this particular node is 1 plus we can just call the recursive function for the left subtree and the right subtree. So this is going to say the number of nodes for the left and the rights. Let's say L and plus R. So if this is not a complete subtree, then we can just return 1 plus left plus R. The L denotes the right left recursive call and R denotes the right recursive call. If this is going to be a complete binary tree, then we can just use the formula to compute to count the number of nodes in that particular subtree. As you can see, this is a tree where it is not a complete binary tree. How can we say this is not a complete binary tree? We can just traverse only to its left. Let's say we can just traverse to its left and count the number level, count the height, and we can also go to its right alone and count the level. As you can see, the height for the left is 4 and height for the right is 3 and 4 is not equals to 3. We can just apply this formula now. 1 plus left recursive call and right recursive call. We can just add it. Now we will be going and standing at this position. Sorry. Now we will be going and standing at this position. If we are standing at this position, we can just calculate the again the left height and the right height by going only to the left and only to its right. And you can see the height in the left is 3 and height in the right is 3. We can apply the formula 2 power 3, which is 8. 8 minus 1, 7. So as you can see, there are 7 nodes in this complete binary tree because this height is equal to its right height. 1 2 3 4 5 6 7. So there are 7 nodes in this complete binary tree. So as you can apply this that formula 2 power h minus 1, you don't want to visit all these nodes. So this is going to return me 7 here. And again we will be going to this right recursive call, and here even here's the similar stuff applies. The left height is 2 and the right height is also 2 and both left height and equal to right height. So since we can apply this formula 2 power 2 minus 1, which is 3. So without traversing these nodes we are returning 3 here. So we will be returning 3 nodes, and here already we are applying this formula 1 plus L plus R. So 1 plus the left is 7 and plus the right is 3. So obviously we will get 11. So for this binary tree, for this complete binary tree, the number of nodes is 11. 1 2 3 4 5 6 7 8 9 10 11. So as you can see, the 11 is the number of nodes present in this complete binary tree. So the time complexity is not order of n here, it is order of log n. Let's say it is much better than the previous time complexity. So now let us try to code this approach very easily. So what we can say is, if my root is not present, then we can just return 0. Else we want to find the left height, which is which we can have a function. Let's say find height, and this is going to go for only its left. So I will have a flag variable true, and similarly we can say we can compute the right height. So find height, I will define the find height function later. Root and just false. So this true and false I'm using as a boolean variable, whether it is going to go for its left or whether going for its right. So we can compute the left and right height by this. If my left height is equals to my right height, so we can apply the formula here. So what is the formula? The power of 2 comma h. H is nothing but the left height. Since it is both are equal, we can use either both variables. So 2 power height minus 1. We can just return this value here. But what if the left height is not equal to right height, so we want to count the count the current node 1 plus. Now we can just go for its left recursive call left subtree root of left plus count nodes of root of right. It is as simple as this. Now we can just define the find height function. Int find height. This is taking the parameter string node star root and a boolean variable flag. I can say it as direction, bool direction. So if root is not present, just return me 0, else I can have a variable height which is going to be initially 0, and while my root is present I can take a temporary node char which is pointing to root. While my curve is present, I can just increment my height plus plus, and based on the direction I should go either the left or right. So if my direction is true, then curve is equal to curve of left, else curve is equal to curve of right. So sorry, and we can just return height finally. So this is going to compute my height easily using this direction variable. We had just written a one function to compute that. So now let us try to run our code. The time complexity here will be order of log n. It is not order of n. Yeah, we get correct answer. Let us try for running other example test cases. We get correct answer. So let us submit the code now. Superb, it gets accepted. So hope you like the solution and let me know in the comments. And let us see in tomorrow's LeetCode daily challenge. Until then, bye.